In order to begin our study of conics, which will basically be new to you, we're going to go back over some stuff we've already done. We're going to talk about an introduction to analytic geometry by studying some things we studied in both Algebra 1 and geometry. So, for example, the distance formula. The distance formula told you how far it was between two ordered pairs on a coordinate plane. The midpoint formula, which was a formula for finding the coordinate of a point that probably bisected some sort of line segment. The slope formula was the steepness of a line between two ordered pairs. It was y2 minus y1 over x2 minus x1. We also know it as rise over run. You also know it as change in y over change in x. So in example 1, we're just going to review really quickly how to use the distance and midpoint formulas. The nice thing about the distance formula is it doesn't matter which ordered pair you call x1, y1 and which you call x2, y2. What I normally do is I call the first ordered pair x1, y1 and the second one x2, y2. The reason I do that is because then it helps me think about how I'm going to plug the coordinates into the formula. So the distance is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. Be careful about the signs of your numbers when you plug into the distance formula. 8 minus 4 is 4. 3 minus negative 2 is 5. 4 squared is 16. 5 squared is 25. 16 plus 25 is 41. So the distance between the 2 points is the square root of 41, or whatever its decimal equivalent is, which is 6 point something. The midpoint, the point that's directly between those two ordered pairs, can be found by adding the x's and dividing by 2, and adding the y's and dividing by 2. And the midpoint is going to be an ordered pair. So 8 plus 4 is 12. 12 over 2 is 6. Negative 2 plus 3 is 1. 1/2 is the midpoint. If I had asked for the slope, you would have done y2 minus y1 over x2 minus x1, and you would have gotten 5 over 4, which means that the line between those 2 points goes up from left to right because it's a positive slope. Next, let's determine whether quadrilateral PQRS with vertices P at negative 4, 2, Q at 3, negative 2, R at 3, negative 3, and S at 1, 5 is a parallelogram. Well, in order to do that, it'd be nice if we'd review some things about parallelograms. This is a parallelogram. This is a parallelogram. A square is also a parallelogram. A parallelogram, the opposite sides of the shape are congruent. Opposite angles are congruent. A rectangle and a square are special types of parallelograms. The diagonals of a parallelogram bisect each other. There we go. The diagonals may not be congruent. Oops, I shouldn't have done that. But they bisect each other, which means that they have a common midpoint. In order to show that PQRS is a parallelogram, there are a couple different things that we can do, some requiring less work than others. The first thing I'm going to do is I'm going to draw a sketch to just kind of give me a visual of what this looks like. So maybe I'll use an actual coordinate plane. I'll use this. So P is at negative 4, 2. There's P. Q is at 3, negative 2. R is at 3, negative 3. Oh boy, really? And S is at 1, 5. I knew something seemed wrong with this. This should be negative 3, negative 2. So I'm going to take Q out here. Should be at negative 3, negative 2. So visually, if you look at this, you're probably going to say it's not a parallelogram. And you're right, it's not. But there are some ways to show that it's not. So, for example, in order for it to be a parallelogram, the opposite sides need to be parallel. In order to be parallel, they have to have the same slope. So, if you find the slope of PS, let's see, 5 minus 2 over 1 minus negative 4, I'm going to get 3 over 5. It should be the same as the slope of QR if it's a parallelogram. The slope of QR is going to be negative 3 minus negative 2 over 3 minus it's not 3 minus 3, it's 3 minus negative 3. So that's going to be, let's see, negative 1 over 6. Well, they're not the same slope. Even though if I went and found the slope of PQ and the slope of SR, they probably are the same. In order to be a parallelogram, the diagonals would have to bisect each other. That means that the diagonals would have the same midpoint. So if I find the midpoint of PR, so the midpoint, I'll make that more of a capital M, of PR would have to be, let's see, negative 4 plus 3 over 2, and 2 plus negative 3 over 2. So its midpoint will be at negative 1/2, negative 1/2. Is it in the same location as the midpoint of SQ? The midpoint of SQ is going to be 1 plus negative 3 over 2, 5 plus negative 2 over 2. So it's going to be at negative 1, comma 3/2. So the fact that they don't have the same midpoint means it's not a parallelogram. So you have to do something more than just draw the picture, look at it and say, well, it's not. Because sometimes we don't draw the nicest picture and it's hard to tell from the actual picture. So these are your options for determining whether 4 points make a parallelogram or not. Because this is pre-calculus, in order to kind of step up the distance and midpoint formulas, we're going to find the distance and midpoint between ordered pairs that don't necessarily have numbers. So we're going to find the distance between CD and C plus 2D minus 1. It works the same way, we're just going to have to do a little algebra. So the distance is going to be the second y minus the first y squared, the second x minus the first x squared. One of the things that I want you to notice is that in the first parentheses, the d's cancel, don't they? And you're left with negative 1 squared. And in the second parentheses, the c's cancel, and you're left with 2 squared. Negative 1 squared is 1, 2 squared is 4, so the distance must be the square root of 5. For the midpoint, it's going to be add the x's, divide by 2, and add the y's and divide by 2. So I'm going to get 2c plus 2 over 2 and 2d minus 1 over 2. The first fraction actually does simplify. It simplifies into c plus 1. The second one simplifies into d minus a half, and that would be the coordinates of the midpoint. In this section, there's going to be a little bit of proof. You don't have to do it in the two-column format that we did in geometry, but there are things you need to know about some of your shapes. So, reminder of some things about triangles, that isosceles triangles have 2 congruent sides. Equilateral triangles have 3 congruent sides. Quadrilaterals, the opposite sides of rectangles, are congruent. The diagonals of rectangles are congruent. All sides of squares are congruent. The diagonals of squares are congruent. We're going to add an extra example. I'm not sure why this isn't on the note sheet because I've always done this problem. Prove that the diagonals of a square are perpendicular bisectors of each other. So, in order to prove that the diagonals are perpendicular bisectors, we have to prove that the diagonals have the same midpoint, and we have to show that they're perpendicular. The slopes of perpendicular lines were opposite reciprocals. Well, how am I going to do that if I don't have a square? Well, we're going to draw ourselves a square. There's a square. All I need to know is that the sides of the square are congruent. So I'm going to make one corner of the square be at 0, 0. So why don't we make this 5, 0? That means that all the sides of the square are 5. That means this must be at 0, 5, and this must be at 5, 5. I could have done this with any number. I could have used 2. In which case this would have been 2, 2, 2, 0, 2. But we're just going to use 5 just because it seemed like a good number. All right, first, I don't care what we prove first. You want to prove that the midpoints are the same? Sure. Let's call this A, B, C, D just kind of to help us out. So I need to show that the midpoint of AC, which is going to be at 5 plus 0 over 2, 5 plus 0 over 2, which is 5 halves, 5 halves, is going to be the same point as the midpoint between B and D. B and D is going to be 0 plus 5 over 2, and 5 plus 0 over 2, which is at 5 over 2, 5 over 2. All right, so I've just proven that the midpoints have this that are the same. So the diagonals intersect at the same midpoint. Now I need to show that the slopes of those two diagonals are opposite reciprocals. So the slope of AC, y2 minus y1 over x2 minus x1, is going to be 5 over 5, which is 1. Which makes sense because this line here is going up from left to right. The slope better be positive. The slope from B to D better be negative because that diagonal is going down from left to right. So y2 minus y1 over x2 minus x1 gives me 5 over negative 5, which is negative 1. The slopes are not only opposite but also reciprocals. Remember that even though it's not a fraction, it really is. It's 1 over 1, and the reciprocal is 1 over 1. So I've just shown that squares, diagonals, are perpendicular bisectors of each other. And that is an introduction to analytic geometry.